The speaker is Bowen Liu from Stanford.
Hello, everyone. I'd like to first start off by thanking the organizers for this workshop. Really nice workshop. So today, it's my pleasure to talk a bit about our recent work on strategies for pre-training graph neural networks. So my name is Bowen, and I'm a chemistry PhD student at Stanford, co-advised by Yura Leskovic and Vijay Pandey. And this is joint work with my fellow PhD student, Weihua Hu, as well as Joe Gomes, who's currently a professor at University of Iowa, Marinka Zitnik, who's currently a professor at Harvard, and Professors Percy, Vijay, and Yura, who are at Stanford. And so because of the time, I'll focus on one particular application in this particular work, and that is in chemistry. But if you were to read our paper, we also do work on in the biology space with protein function prediction. So this is the motivation for our chemistry application. And so this graph shows the number of drugs that are developed per unit $1 billion. And you can see that over the past 50 years, it's actually been decreasing exponentially. And this rule is often jokingly called Eroom's law, which is basically Moore's law in reverse. And so this motivates us because it makes us think, is there machine learning tools that we can develop to help make this drug discovery process more efficient? So the particular problem that we focus on is molecule property prediction. And the task is essentially, given a molecule, can you predict its property, right? Whether it's toxic or not, or whether it binds to an enzyme or not. And the motivation here is that actually it's very expensive and time-consuming to actually experimentally test molecules. And so ideally, if you have a model that could make these predictions very accurately, then you can run these virtual experiments much quicker and cheaper. So there are quite a few challenges in molecule property prediction. The main problem is that there just isn't a lot of label data out there because, as I mentioned previously, it's expensive to generate these labels. And so empirically, we see that a lot of these machine learning models usually overfit to these very small training data sets. The other challenge is more in how we use these models. Usually when we use these models, we want to use it for scientific discovery, where kind of by definition, the examples that we see during test time can be very different from those seen during training. For example, we might want to make predictions on molecules that are new and that are structurally very different to what we've seen previously. And we know that a lot of these models usually perform very poorly in these prospective settings. So it seems, transfer learning could be a natural solution to this, right? Because, first of all, we have a lot of unlabeled data out there, right? We know a lot of molecules that have been made previously. There's also quite a large amount of labeled data, but usually for other kinds of properties or other kinds of tasks that are not your current task of interest. But the issue is just naively performing transfer learning, for example, multitask learning or pre-training, can often lead to worse results. This is called negative transfer, and the issue is a priori, it's often very hard to know whether transfer learning can help or not. So our work is basically a systematic exploration of pre-training for graph neural networks, in particular for graph classification. And the spoiler here is that we find it's important to combine both a node level and a graph level pre-training approach to both reduce negative transfer and also improve generalization performance. So just very quick recap of how we can do graph level prediction with GNNs. So in the message passing paradigm, this happens in 2 steps. The first step is you do message passing where you update each node feature with information from its neighbors. And after a few iterations of this, you pull together your updated node representations to get your final graph representation that summarizes your graph. And then you use that graph representation to make your prediction. One of our key insights is that it's the node embeddings that are the building blocks for this prediction process. And so it's important to have good node embeddings that capture the local structural similarity, can be aggregated into graph representations that have useful information. And also because the graphs that we look at are not just abstract graphs, but they're actually real-life objects, it's useful to incorporate domain knowledge as well. And so this cartoon kind of shows at least our hypothesis for what makes kind of robustly transferable graph representations. And so we differentiate between node-level pre-training and graph-level pre-training, where we include the training signal. So node-level pre-training, we use the updated node embeddings to make a prediction, whereas for the graph-level pre-training, we use the final graph representation. And so here we're just illustrating the node embedding space and the graph embedding space, different node embeddings can be aggregated to form graph embeddings, and then different colors represent semantically different nodes and graphs. And so if you look at the center column, this is just applying graph-level pre-training, which is what people naively do. For example, pre-training on other molecule properties. And we're saying that if you just do this, then obviously your graph embeddings are embedded well, but there's no guarantee that your node embeddings themselves are meaningful. And this means that perhaps in your downstream task, if it's very different to what you pre-trained on, then maybe you won't be able to generalize to those downstream tasks, and negative transfer can occur. If you look at the left one, then if you only apply node-level pre-training, obviously the nodes are well embedded, but the model won't know how to aggregate them together to form good graph embeddings. And so basically we're showing that we're saying it's important to do both node and graph level pre-training for robust transfer. And so we come up with two unsupervised node-level pre-training approaches to try and which allows us to capture information from like a natural distribution of data. So the first one is context prediction, where we apply the distributional hypothesis to the graph space. Here, we're using a subgraph embedding centered at the red center node, for example, to predict its surrounding context embedding, which is kind of this little donut that's right beyond it. And the idea here is that in order for the model to do this task well, then it should be able to learn node embeddings that capture the local graph structure. Right, for example, atoms or nodes that are surrounded by similar structure should be embedded closer together. And this kind of makes sense in the chemistry space, where we know that the chemical property of an atom kind of depends on its environment, right? The second pre-training approach, node-level pre-training approach, is we call attribute masking. And this is basically, we mask like a node or edge attribute, and then we use the node embeddings after a message passing to predict what the masked attributes are. And the idea here is that if the model can perform well in this, then it must somehow capture some kind of domain knowledge. For example, in chemistry, maybe the valency. So overall, our approach is, so we used a recent graph neural network architecture called the graph isomorphism network, which is one of the most expressive architectures. And for the training procedure, we first start with node-level pre-training on unlabeled data, and then graph-level pre-training on labeled but auxiliary data. And then after we have our pre-trained model, we fine-tune on the downstream data. And so in one of our applications for molecule property prediction, the task is essentially given a molecule, predict a yes or no for a series of properties. And we use very simple atom and bond node and edge features here, where we include just the atom type and the bond type and some stereochemistry information. And so we pre-train on, for the unlabeled data, we have 2 million molecules from zinc, which is a commercially available database of molecules that you can actually buy, and so they exist. And for the labeled data set, we use about 500,000 molecules from Kimball. That includes about 1,300 different biological assay information. And the downstream data, we use 8 different data sets from the MoleculeNet benchmark, which is the standard benchmark in molecular machine learning. And in order to look at the generalization performance, we perform a scaffold splitting procedure instead of random splitting. And so here we ensure that the molecules that we have in the test set are very structurally different to the ones in the training and validation sets. And so this is a small snippet of the results. In terms of context prediction and graph level supervised pre-training, we show that over the average ROC ABC over all 8 tasks has the highest improvement if you combine the no level and no level and the graph level pre-training, which is in green. Obviously, just naively applying graph level supervised pre-training also results in performance improvement, but definitely combining the no level and graph level strategies result in a higher performance increase. If we were to look at the results in more detail, split over the 8 different data sets, then we see that in orange, just applying supervised graph level pre-training, we have an improvement in 6 of the 8 different tasks. But for 2 of them, ClinTox and HIV, we result in a small decrease in performance, which here we're saying is negative transfer. But if you combine, the context prediction and the graph level pre-training, then we kind of reduce this negative transfer. And these results are consistent for also the biology application as well. So in conclusion, our work kind of explored pre-training strategies for graph neural networks for graph classification. And we showed that it's important to combine both the node level and the graph level pre-training to reduce negative transfer and improve generalization performance. And I briefly showed a hypothesis that we have for why combining these 2 approaches can lead to robust graph representations. So I'd like to thank all my collaborators who are involved with this work and all the funding sources for the labs. Thank you.
Any questions from our audience? We have time for like 1 or 2 questions.
Hi, thank you for the presentation. I thought it was really interesting. I have a question for you in the representation of the molecules that you showed. Mm-hmm. How do you delineate between secondary and primary bond order? Because an aliphatic hydrocarbon is going to behave differently than a secondary. Like you can't alkylate on a aryl chloride like you can on a benzylic chloride. Mm-hmm. And how do you account for things like stereochemistry, which also change the reactivity and therefore the cytotoxicity of your molecule?
Yeah. So that's kind of incorporated in both the node and bond features. And so for each atom, we also, or at least here, so here it doesn't actually directly incorporate this, but through the bonds, we have edge types, single, double, triple bonds, aromatic bonds. And for stereochemistry, we include the chirality of the atom as well as the bond stereochemistry in the edge feature. Okay,
and did you see any dependence on those one-hot features in your output?
So we only, we didn't explore different features. We tried to use the simplest features available. So just atom type, atom stereochemistry, bond type, bond stereochemistry.
Cool. Thank you.
Thanks.
Okay. So now we're going to have our second contribution talk. The title is going to be Variational Graph Convolutional Network. And the speaker is Edwin Wong from Cyro Data 61.
Hi, everyone. So my name is Edwin. I'm a principal research scientist at Cyro Data 61. And this is joint work with Luis Tiao Panteli Salinas, and Harrison Nguyen. OK, I guess it's fair to say that I'm relatively new to this world of graph neural networks. So I'm sort of a Bayesian person. So the first time I encountered this world, I asked myself, how come graph neural networks assume, or most graph neural networks assume that the graph is 100% reliable? Okay? So by thinking this way, I thought about a large spectrum of problems where thinking in this way could help. For example, if you think about learning in noisy regimes, for example, if the graph is noisy, in many applications, the graph might be loosely related to the problem, to the supervised learning problem. And finally, in other applications, the graph can be built sort of in Adobe Basic. So think about building a graph based on features, and that's sort of commonplace in many applications like computer vision and so on. So really, one of the things I thought about, or the first thing I thought about is, how about we incorporate uncertainty about the graph itself? And how can we do that in a principled way? OK, so let us formalize a little bit this problem. So we are talking about a particular problem that is graph-based semi-supervised classification. So in this case, we have n instances. And we're going to have features for those instances. So we have these features are d-dimensional. So we have a matrix of features that is n times d. Each of those instances are going to correspond to a node in the graph, or a possible graph that we're going to be given. And we also have labels. So the labels can be visible labels for some of those nodes or for some of those instances. And we denote them with YV. And the labels can be hidden as well, and we denote them with YH. Okay. And in this particular problem, it's a classification problem, so we have each of those values can be one of C classes. Okay. Now, if you think about the standard graph neural networks, we can think about we are also given a graph, and we can represent that graph with an adjacency matrix that is, let's say, n-dimensional. It's a binary matrix. In this particular problem, we're going to focus on undirected graphs. And for reasons that will be clear later, perhaps because we're going to use graph convolutional networks, we're going to augment, or we're going to add to this matrix a diagonal term, an identity term. In some way, we are augmented our adjacency with staff loops. And we're going to compute the degree matrix of that new adjacency by simply summing the corresponding elements. Okay. So I hope perhaps most people, or at least a large number of people in the audience, know about graph convolutional networks proposed by Keith and Welling in 2017. And essentially, we have at the first layer of the network, we have the features. And at every intermediate layer, what we do is we simply use that sort of version of the adjacency matrix in order to do one hop through the network and do some sort of aggregations of the features at the corresponding layer. Okay? And then we linearly combine those features with some weights, and there are the parameters for each of the layers. Okay? Now, this H here is a nonlinearity. So if we think about intermediate layers, that can be, for example, a ReLU activation. Or if we think about the output layer, that can be a softmax. In this case, it's a softmax. So I'm going to refer to the parameters of the GCN as theta. And in the standard method, or in the method proposed by Keith and Welling, they were estimated by using, or by minimizing the cross-entropy error. Okay. Now, one of the things that we found in our experiments is that the performance of GCN, or standard GCNs, really degrades significantly under noisy regimes. If you add noise to the graph, to the original graph, the performance degrades significantly. So again, we come back to this goal of how can we incorporate uncertainty about the graph itself, and in addition to that, how we can have alternative methods to do estimation of the parameters of the augmented model. And perhaps for me, at least, the natural way to think about this problem is really to formulate a joint distribution over everything. And after you do that, you can try to do approximate inference. So I'm going to focus on how to do that. So the first component of our model is really the likelihood model. I'm going to go through this one really quickly. I hope people have seen GCNs before. So we just use, for the likelihood model, a simple two-layer GCN. So at the first layer, we simply apply the propagation rule, the GCN propagation rule. we do a ReLU transformation, and at the next layer, we apply the propagation rule again, and then we do a softmax. And if we put a categorical distribution on that using the softmax output, then we have our likelihood model. Now, the main difference with standard GCNs is now, rather than assuming that we are given A, that we are given the adjacency matrix, now we're going to say that this A is a random variable. Okay? Now, the key thing here is we're going to say that this random variable is going to have a prior distribution. Okay? And now this prior distribution is going to be constructed using the observed, potentially noisy, and reliable adjacency matrix. Okay. So we really, we start thinking about things in very simple terms. We're going to say, let's say that the joint distribution over that adjacency matrix, the joint prior distribution, factorizes over the entries of the adjacency. And each of the individual distributions is simply a Bernoulli distribution, okay, with some parameters rho, and I say rho 0 to denote the prior. Now, there are many ways in which you want to encode prior beliefs about your problem. You might want to encode perhaps sparsity and so on, right? So really, one of the things we really wanted to do was simply to say how much we should trust this auxiliary graph. I'm going to denote the auxiliary graph just now with a bar to distinguish it from the random variable A, okay? So we came up with this incredibly, and I want to emphasize the word incredibly simple construction. So we're going to say that the parameters of each of the Bernoulli distribution is simply a linear function of that given adjacency matrix. Okay. Now, the important thing to note here is that we have two happy parameters. One of them is rho 1 bar, and the other one is rho 0 bar. And I refer to those things as smoothing factors. And essentially, they're telling us, how much I believe, what are the probabilities of presence, rho 1 bar, or absence of a specific link. Okay. Now, we also thought about and implemented hierarchical approaches for this problem. But in fact, they didn't provide additional benefits. What did provide additional benefits was actually to focus on the inference. So now we have our likelihood. Now we have our prior. Now what we want to do is to estimate the parameters of our model. Yes. So we're going to do that. How can we do essentially graph structure estimation via posterior inference? Okay. So now if you think about this problem, it's a bit like crazy to think about this, right? Because you want to estimate a posterior over graphs given your observed data, right? So clearly you can think this is completely intractable. It's a very large combinatorial space of graphs, right? So one possibility simply is to be variational about this, okay? And perhaps one of the main advantages of being variational about this problem is really variational inference provides us a compact representation of the posterior. So if you can think about other things like MCMC and so on, then it really is not practical to have a large number of samples around, a large number of samples of graphs around, right? So what we're going to do, or what variational inference entails, is we're going to define an approximate posterior Q5 over the adjacency matrices, over graphs. And we're going to estimate the parameters of that posterior. Those parameters are going to be denoted with phi by maximization of the evidence lower bound, okay? And people who do variational inference, they know that this is equivalent to minimizing the KL divergence between the approximate posterior and the two posterior distribution. Now, the first step, we need to define a variational distribution. Then it's perhaps sensible to say, well, my variational distribution can be a factorized distribution similarly to our prior. I'm going to say also that each of the individual distributions is a Bernoulli distribution as well, now with some parameters rho. Now, the naive way to think about this problem is to say, I'm going to have a completely free parameterization for the posterior, or for the approximate posterior. Now, here I'm showing you the negative evidence lower bound. So in this case, we want to minimize this quantity. And this is as a function of the number of epochs during training. Okay. And this blue line shows you what happens when you have a free parameterization. I guess the summary is really a very hard optimization problem to solve. One way to think about this is perhaps the factorized assumption on the posterior is very strong. Okay? So what else can you do? So we propose if we simply do a smooth parameterization of the posterior. One way to think about that is you somehow embed your posterior distribution into some latent space. So for every node, we're going to have a latent representation that is small d-dimensional. And we're going to say the parameters of each of the Bernoulli distribution is simply going to be a function of the dot product of those latent representations. Okay. Now, the variational parameters, rather than being free parameters, they're going to be exactly those latent representations of every node. Okay. So in some sense, what we have now is we have a shared representation for the posterior. Now, if you look at the negative evidence lower bound, is this orange line here. So somehow, because we are doing a stochastic optimization, somehow it does look like it's behaving how we expect it to behave. There's an additional technicality. It's about discrete versus relaxed. So if we have discrete priors and posteriors, then we need to do something like square function estimator to estimate the parameters and so on. So what we do is we do a relaxation, a continuous relaxation using the binary concrete distribution. And the binary concrete distribution, I'm going to say it has here, in this case, has parameters lambda. These are the variational parameters, and has a temperature parameter tau. So as you make tau go to 0, it tends to the actual discrete distribution. But it's going to help us to actually do the optimization. OK, so how do we do the actual estimation of the posterior parameters? We maximize the evidence lower bound. So we have a KL divergence term between the approximate posterior and the prior, in this case. And we have the expected likelihood term, where the expectation is computed over the approximate posterior. As I said before, you can have a discrete Bernoulli posterior and discrete prior. In this case, the KL is very simple, and we can estimate the expectation or the ELL term using Monte Carlo sampling. If we use the binary concrete posterior, then we need to relax both the prior and the posterior to maintain the lower bound. And what we do is we use a more numerically stable parameterization of the binary concrete distribution using logistic distributions. So what we can do is we have an auxiliary variable B that is sampled from a logistic distribution with location given by this expression and scale given by this expression. And then you sort of squash those samples through a sigmoid function. And then you get samples from the binary concrete distribution. Okay. Now, very quickly, we do experiments on several data sets, 2 citation networks, and a social network data set. I'm going to show you some results on the citation networks. So as I said before, one of the applications we use is sort of the noisy regime. So in this experiment, what we're doing is we're adding fake links to the original graph. So this is a citation network. So think about papers. Papers have features, and the graph is given by the citation network, and each paper corresponds to a node. And each of the nodes has a label that is the class to which the paper corresponds to. Okay. So what we see here is the accuracy of several methods as a function of the corruption factor. And the corruption factor here is simply the ratio of the additional links we put in the graph relative to the number of true links. So and here is our method, that is BGCN, the relaxed version with different smoothing factors here. And here we have GCN, the original GCN method, graph attention networks, and graph sage. So what we notice is as you add more noise, so GCN and the other methods are really less robust to that noise than our method. And for example, in this case, for the CiteSeer data set, when you go beyond a factor of 2, you can see the gap in performance. Similar results are obtained for the Cora data set. And also, perhaps it's worth highlighting the comparable performance of our methods in regimes where no noise is added, for example, or even when no graph is given. So I'm going to leave you here with the conclusions, and perhaps just simply to highlight the reference implementations on this link. Thank you very much.
Any questions? Any questions? I have a short question. Yep. So you're saying that, OK, so when we try to model the probability of the graph, right, we assume every link is independent with each other. Yes. But in practice, for real-world graphs, actually there's kind of other constraints. For example, a friend's friend is more likely to be friend. So do you have an idea how we can encode that and further enhance this model?
Yeah, That's a very good question about independence assumption. There are two assumptions. One is in the prior. And I guess we also have thought in the prior is strong. What we've done is we really wanted to incorporate very simple information that you can have a priori. For example, how much I should trust the presence or absence of a link. You can have hierarchical a prior, so that sort of relaxes the assumption. The assumption in the posterior, we sort of go around that problem by having that also sort of what I call a smooth parameterization. Yeah.
Okay. So let's thank our speaker again. So now we're going to have our third contribution talk. The title is Probabilistic End-to-End Graph-Based Semi-Supervised Learning. And the speaker is Mariana from INRIA Lilly Nord Europe. Welcome.
Hi, everyone. My name is Mariana Vargas. I am a PhD student at INRIA. What I'll present here today is some preliminary work on graph-based semi-supervised learning based on autoencoding variational-based. I did with my supervisors, Aurélien Bellet and Pascal Denis. To start with a little bit of background, when we say semi-supervised learning, we mean methods that aim at estimating a target variable, assuming only a small portion of data have labels. In the transductive setting, this boils down to finding the missing labeling, here indexed from L+1 to N, and this is the setting we're interested in. And semi-supervised learning methods aim at leveraging unlabeled data. So there's a particular case of semi-supervised learning methods that are graph-based, in the sense that the way we leverage unlabeled data is by representing the underlying structure of the data through an adjacency matrix that basically encodes pairwise relationships between the points. So this is what a generic algorithm would look like. We input our training set, our adjacency matrix, and we get an estimation of the labels. Now, the problem is that for many tasks, there is no readily available graph, or there is one, but we don't know it. So in general, one could compute an heuristics graphs like k-nearest neighbors or RBF kernel, but we don't want to rely on heuristics. So what we're going to do in this work is to jointly learn the graph and the parameters of a prediction model. The contribution is mainly twofold, because in the one hand, we propose a semi-supervised algorithm method that deals with the case where there is no knowledge about the underlying structure of the data, but this algorithm also learns a task that is a graph that is meaningful for the task at hand. So how do we do this? You'll find here some similarities with the previous presentation, because we use the Bayesian machinery. We consider the graph to be an unseen latent graph. This means that our edges are unobserved random variables. And we consider the target variable to be generated by a random process parameterized by theta that depends on the data and the graph. Now, in the Bayesian context, this unseen latent graph, it's also a set of parameters for this random process. And as such, it has a posterior distribution. For even fairly simple choices of model, our posterior distribution might be intractable. So we choose to frame this problem using the autoencoding variational-based framework. To use this algorithm, we have to define two components: an encoder that will approximate our true posterior with some distribution Q with parameters phi, and the decoder that is our likelihood with parameters theta. So this is how the generative process looks like. To generate the labeling, we will feed the encoder, run the encoder to produce a distribution over the graphs. We will sample a graph. We will feed that graph and the data to the decoder to obtain a distribution of our target variable. And here I want to point out another crucial reason for using autoencoding variational base. which is the fact that it permits to backpropagate the error through the sample graphs. So think that if we were using plain variational inference to approach this problem, we would have to approximate the integral from the previous slide by sampling graphs and, let's say, aggregating them. But here, at the end of the computation of this algorithm, not only we get our optimal phi star and theta star, but also a particular instance of the latent graph. To optimize, we have to maximize the evidence lower bound, which is a quantity that lower bounds the log marginal likelihood. So in this case, that would be the target variable provided the data. The rightmost probability here is the prior over the graph, which is user input, and it encodes our prior beliefs about the graph, like sparsity or any property. In this context, we can think about this as a minimization of the reconstruction error we get from producing an estimation through this encoder-decoder machinery. For the experiments in this work, we chose the encoder to be a Bernoulli distribution. So each edge will be drawn from a Bernoulli distribution parameterized by some function f that follows a message-passing graph neural network model. This recursively produces node and edge embeddings. It hops in the neighborhood of a node, aggregates the neighbors, and produces a node embedding, and then produces an edge embedding by concatenating two node embeddings. So basically, this will produce, in the case of the fully connected graph neural network, n-square edge embeddings, which we will use to produce our parameters. And note here that we've made a simplifying assumption by asking Q, the distribution Q, to depend only on the data and not on the target variable. Our decoder, in this case, it will be a categorical distribution parameterized by a graph convolutional network, which is a state-of-the-art semi-supervised algorithm. It also recursively defines data representations, and we will use the final data representation to produce our parameters. In this particular case, the reconstruction loss will be the cross entropy between the estimation and the ground truth, the estimation limited to the label set. And the KL divergence for a Bernoulli prior will have this closed form. In this case, the Bernoulli prior will encode the sparsity of the graph. So let's say if I ask my prior to be 0.01, I am asking the graph to be very sparse. We run experiments in 5 data sets, NLP data sets mainly. We enforce the semi-supervised setting by picking only between 2 and 3% of label data. We compare our method with 3 supervised baselines, logistic regression, SVMs, and feed-forward neural networks, and 2 semi-supervised baselines consisting in graph convolutional networks fed with heuristically computed graphs, KNN and RBF kernel. We tune the main hyperparameters for every method. At the first glance, from this table, what we can see is that we systematically outperform the semi-supervised baselines. So to conclude, we presented a semi-supervised learning algorithm based on autoencoding variational base that produces an estimation of the missing labels, but also a graph that is meaningful for the task at hand. We showed that we achieve considerable gains over the baselines in general. And as for the ongoing and future work, we're working on testing different distributions over the graph, other than Bernoulli, an inductive setting, meaning handling unseen examples, address scalability, which is a problem on itself, actually, and definitely compare this method to something proposed by Franceschi and other authors early this year, which their setting is quite similar in the sense that they also have a probabilistic view of the graph, and it's also Bernoulli, but they use a B-level optimization framework to compute an hypergradient. So they treat the Bernoulli parameters as an hyperparameter. We think that we have two advantages, but we have to see. First, the fact that we can input a prior over the graph. They cannot do that. And second, we only need access to one validation set. They need two validation sets. So we potentially have access to more data. And that's it. Thanks.
So we still have time for one or two questions. Any questions? No? OK, so you didn't show in your experiments like how the performance will change when the percentage of labels are given. So do you have any results on that part?
Well, actually, no. The fact that the supervised baselines work quite well probably means that the very few elements, labeled elements we picked were already very informative. And that's one reason for us to move toward more naturally semi-supervised tasks. But we kind of took a very standard percentage of unlabeled data. This is what, in general, the community uses to compare methods.
OK, I see. So let's thank our speaker again. So next, we're going to have our invited talk, which the title is like Representation and Synthesis for Molecular Graphs. And the speaker is Wengong Jing from MIT.
All right. Hello, everyone. I'm Wengong. I'm from MIT. Today, I will be talking about representation and generations for molecular graphs. This is in collaboration with my advisor, Tommy Yakola, Regina Barzilai, and my colleagues, Kevin and Kyle. Sorry, just a minute. Well, maybe I should unplug. It just somehow disappeared. So. Yeah. OK, sorry for still some problems with the slide. Right, so today I will talk about generation and the representation for molecular graphs. What are molecules interesting for machine learning? Well, so molecules are graph structures with rich semantics. Let me give a quick overview or intro of how molecules looks like. As you can see from the slide, each graph is molecules are graphs, where each node is an atom and labeled with its atom type. Each edge is a bound labeled with its bound type. Molecules also have motifs. There are some certain groups of atoms that form together as a substructure, which has specific chemical meaning. So together, they give rise to a variety of chemical properties, such as solubility and toxicity. So properties may depend on intricate structures. As you can see from this molecule, the structure is quite complex. It is an antibiotic that we often use. The key challenge here for machine learning is to automatically predict chemical properties and generate molecules with desired characteristics. So there are a lot of interesting problems centered around molecules and chemistry. And we have been really thinking hard how to solve these problems in an interesting and principled manner. Of course, today I cannot cover all of them. I will talk primarily about deeper into drug design. This will involve a lot about graph representation learning and also generation of molecular graphs. Our ultimate goal is to sort of automate or accelerate drug discovery. I know this is a very ambitious claim, but and there are a lot of challenges. The first challenge is the representation and prediction. How can we learn to predict molecular properties from the structures? So one standard approach is to use graph neural networks to embed molecules into this continuous vector representation and then predict the chemical properties out of that representation. It has achieved good empirical performance on a variety of tasks, but in theory, is GNN expressive enough to predict the molecular properties? A lot of recent work has shown that basic GNNs are not expressive enough. There is something missing in the representation that is learned from the GNNs. So in particular, this is a work from my friend Vikas Garg and my advisor, and also Stephanie. In particular, it can be shown that a GNN with permutation invariant readout functions cannot decide many things. For example, the length of the shortest or longest cycles, the diameter of the graph, or presence of conjoint cycles that are cycles that attach together, and many others. Most of the results also apply to a variety of graph architectures like MPNNs. So many of the cycle information or substructure information is kind of lost in this continuous representation. But these are quite important for predicting chemical properties. This kind of motivates us to go just beyond simple GNNs by adding those missing substructure or cycle information back to our architecture. So to this end, we propose to represent molecules at multiple levels. For example, in this case, we can represent molecules in 3 levels. The first level is the original molecular graph. That's the same as the simple GNNs. And I can run standard graph convolution on this graph, and each atom receives a vector representation. It is easy to create a dictionary of substructures by extracting them from an existing database of molecules. For example, here I'm listing a dictionary of substructures that contains bounds or cycles, which in chemistry we call it rings. So based on these substructures, I can construct a coarsened graph, a coarsened version of the original graph, by pulling these atoms together into substructures. So we call this coarsened graph a substructure graph. Each node in this layer is labeled with its substructure type, a one-hot encoding in the dictionary. And we draw edges between 2 substructure nodes if they intersect with each other. I can slightly tweak the substructures to be more fine-grained by marking what are the intersecting atoms that in between these nearby substructures. For example, in this case, I have two rings that have two intersecting atoms, and mark those atoms in the substructure label. So these are the red dots that I highlighted on the slide. And I can do the same thing for others. By doing so, I'm not losing information too quickly from this pooling step. With the marked these red dots, or these intersecting atoms, I can still reconstruct this, the original molecule from this coarsened graph representation. And I can run, again, just standard graph message passing network on this substructure graph. In addition, I can propagate the atom embeddings learned from the previous layer to the substructure graph while I'm running the message passing. Now each substructure also receives a vector representation. At the top layer, I can drop these fine-grained attachment information and just look at the substructures. So this further coarsens the graph and put more emphasis on the substructure identities. What are the substructures that are there in the molecule? We will show later, so I can similarly run this message passing network on this layer with additional message vectors from the lower layers. This type of hierarchical message passing network has been proposed in other contexts, for example, Yin et al. For social network modeling, node classification tasks. We will show later that this type of hierarchical modeling is also beneficial for graph generation tasks. But let me just give a sort of a quick experiment on how these property prediction models works. Here's an example experiment for solubility prediction. It is a regression task, and so this lower the better. And you can see the raw GNN that's on the far left actually does not perform very well. As I mentioned earlier, simple GNNs does not memorize or does not remember what are the cycles or other structural informations in the representation. To make the GNN or raw GNN actually work, you will need to add these extra features that is in common practice, what we do in practice. For example, for each atom, you need to specify features like whether this atom is in a cycle, whether this atom is in an aromatic ring, etc. You can add however many structural features you want. And once these features are added, you can see the performance does get significantly improved. And that's why most of the simple GNNs does work well on these benchmark data sets. The performance can be further improved by this hierarchical modeling, but without using those features that I mentioned. The improvement here is not very big, but I will later show that this hierarchical GNN will give much larger improvements on graph generation tasks. But just before I go into that, let's see how these property predictors are useful in real-world drug discovery projects. So if we can accurately predict the molecular properties, then perhaps we can use that to screen a large database of molecules and to try to see what kind of molecules have the desired characteristics. So let me briefly describe what we did for an antibiotic discovery project that we collaborated with biologists at MIT. So specifically, we trained a model to predict the inhibition against E. coli. E. coli is just some bacteria. And we trained our model on 2,000 measured compounds that's given from the biologists. So we trained this model, and then we used that to screen in total 100 million compounds from the zinc library. So it's a big database of molecules. And we give the biologists 15 molecules that are within the top prediction, that has the top highest predicted inhibition score. Of course, we kind of selected those 15 molecules to be structurally diverse so that we are not just exploring one part of the chemical space. And amazingly, some of them actually are validated to be inhibitive in vitro in the lab. And one of them demonstrated strong inhibition against not only just E. coli, but also other bacteria species like Abamani. All of them are new antibiotics that is distinct from the existing ones. Perhaps this might sound a bit natural because we are training on the molecules with measured properties. It should be able to find molecules that has good inhibition scores. But to the biologists, that was actually pretty surprising, because in the to them, the antibiotic discovery is a very challenging task. It's facing a lot of difficulties because most of the low-hanging fruits are actually just gone. So by human kind of intuition or experience, nowadays it's hard to just find novel structures that has good inhibition against some bacteria. But we can show here, using the computational models, we can accelerate this discovery process. So far, I have talked about property prediction and the graph representation. That's just one pillar of this whole big picture of accelerating drug design. The other challenge is about the generation and optimization of molecules. In many other cases, we want to discover new drugs that is not in the existing library. And the previous brute force screening approach is not ideal here. We want to discover something that is new, or at least not to the standard chemical space that we care about. The task is challenging because it often requires us to optimize multiple properties. So this is called de novo molecule optimization. Here, the optimization means to modify a given molecule so that it satisfies given design specifications. In many real-world drug design cases, we are often faced with molecules that have some good properties, but they lack some other crucial properties. So it's not perfect. And the job of many medicinal chemists is to, in those pharmaceutical companies, what they do is try different modifications of these compounds and see which work better. For example, let me just illustrate what this really means. So for example, you can modify this compound on the left to be more drug-like while staying potent to some disease. I can also try to modify this compound to be more soluble while remaining potent to some disease. So in most cases, the task of this de novo optimization seeks to learn a molecule-to-molecule mapping, or in other words, a graph-to-graph mapping. The output compound is constrained to be structurally similar to the starting point because you don't want to destroy the good properties that they already have. Since the input and output graphs has to stay similar, this molecule optimization can be viewed as a graph-to-graph translation problem. To model this translation task, we can use a standard encoder-decoder architecture, but all operating on graphs. So the encoder maps a source molecule or a source graph into a set of vectors, and the decoder seeks to generate a new graph from those vectors, which has better chemical properties. So the task is quite similar to machine translation in natural language processing. The training set consists of source-target molecular pairs that demonstrates what kind of graph transformations can improve the chemical property that you care about. Such molecular pairs can be extracted from the molecule databases as long as you have the properties labeled. Basically, you can just pair up those molecules that are structurally similar but with distinct properties. The key challenge here is the graph generation. How can we generate graphs in a way that kind of respects inductive biases of molecular graphs? So here, again, we want to turn to this hierarchical modeling that we described earlier. This GNN encoder we can use to map the source molecule or the input molecule to a bag of vectors that is shown on the left. This representation, we think, is more expressive because it incorporates additional substructure or motif information. The question is, can we do similar thing for generation? Can we also generate molecules with substructures in mind or those motifs in mind? So in the following, I will show a hierarchical graph generator for graph generation. Intuitively, the decoding process is kind of similar to the reverse of the encoding process. So the decoder seeks to incrementally construct the hierarchical graph of the molecule that I just mentioned. It incorporates, it has the substructure levels and the original molecular graph. In the beginning, the model predicts what is the first substructure and initialize the decoder state like this. At each decoding step, I kind of apply this hierarchical message passing to learn these vector representations for all the substructures and atoms in the graph. The model seeks now to expand the molecule by one substructure. How do we do that? Well, remember, we have this vocabulary of substructure or motifs that we kind of constructed a priori. And this can be just naturally cast as a classification task, predicting the right substructure in front of a dictionary. Once we predict the next substructure, I can put it into the top layer substructure graph. The remaining question is how to attach those substructures together. Even though we have the new substructure, it's still disconnected from the current graph. At the top layer, the key is to predict what are the attaching points in between. Well, this is not a hard task. Since each substructure is quite small, there is only a limited number of ways to attach them. We can first predict what are the attaching points in the new substructure. In this case, there are 6 different attaching configurations for this ring that I shown on the right. So predicting the attachment can also be cast as a classification task. Once we find the correct attaching configuration, we can update this second middle level attachment graph. Finally, I can just find what are the corresponding attaching points in the current molecule that has been generated. This prediction step is kind of similar to the previous step, but based on the atom vectors learned by this hierarchical GNN. So in this case, the model predicts those blue circles that will correspondingly be attached to the red circles on the slide, and we will just merge them. And we will have this one-step generation with this new molecular graph. Since now the graph has changed, I need to update the atom and substructure embeddings by running the hierarchical GNN. There are some technical details that I kind of omitted due to the time limit, but there is a way to avoid recomputing all the vectors from scratch, so the decoding process is still efficient. I can just recompute the atom or substructure embeddings that are involved in the change. Now the model will just repeat this process until it decides to stop. As you can see, this kind of intuitively is just a reverse of the encoding process that I mentioned earlier. So that's the basic picture of this encoder or decoder architecture that we can use. Of course, you can make many extensions. For example, you can incorporate variational inference to encourage the output diversity. This is important because there are many ways to improve, to optimize a given molecule. The diversity can be achieved through a latent vector z, a latent variable that is learned by variational inference. If you manipulate this latent variable here, it will guide the model to generate different compounds. You can also incorporate the design specs into the model to make the process conditional and controllable. As I mentioned earlier, in the drug discovery, we often care about optimizing multiple properties rather than just single ones. This is important also because different optimization tasks seek to optimize different combination of these properties, and these tasks naturally become correlated with each other. For example, in one application, I may want the design spec to be generating something to be more drug-like while active to DRD2. So here, DRD2 is a protein that regulates synthesis and the release of dopamine that is important for the central nervous system. So, but in other applications, I may want the output to be still drug-like, but DRD2 inactive in order to avoid some side effects. The model generates different molecules when conditioned on these different design specs. So I will give a quick overview of some of the experiments that we did. The first experiment is on the DRD2 optimization. Here we can see the proposed hierarchical model that I just described on the far right. It achieves the state-of-the-art performance on this benchmark. We also compared it with atom-based generation method that generates the graph atom by atom or node by node. In this case, we can see a lot of improvements by utilizing this additional substructure information. On the other task, drug likeness optimization, we also see similar trends. Another experiment, we wanted to do some multi-criteria optimization. Here we evaluated our model using two different criteria. On the left, you can see the criteria for the generated output is to be both drug-like and DRD2 active. On the right, the criteria changes to drug-like while not active to DRD2. In both cases, our model does outperform all the other baselines. But you can see on the left, the criteria is very challenging because only 1.6% of the training data in our data set are both drug-like and DRD2 active. So as you can see, this is, all the model performance is kind of low because of lack of data. And you can already see the challenge of multi-criteria optimization. I'm just stacking two properties, but I can stack more. And we also did some more ablation studies to assess how individual parts contribute to the performance. Graph-to-graph is a very new and challenging task. There are still many ways to improve upon the basic encoder-decoder model that I just touched upon. Generating complex objects such as molecules is hard in general, especially when the training set is kind of small. And in this case, our training set is usually around 50K to 100K molecular pairs. It's nothing compared to machine translation in NLP that is typically trained over millions of sentences or even beyond. But on the other hand, assessing the quality of the object, the generated compound, is substantially easier. I can easily predict the chemical properties as long as you have it. So this kind of motivates us to do something to leverage this property predictor to guide our generation process. And we call this a target augmentation. The basic idea is to use the property predictor to generate additional self-supervised data for this translation model. The objective now becomes the log likelihood of generating something, generating a molecule Y that satisfies the design spec. Now, the difference between this objective and the previous one is that the generated molecule Y now becomes a latent variable. And this objective can surprisingly be solved by EM, even though you have a large structural output space. The E step generates candidates from the current molecule, from the current model, and you can filter or reweight using your property predictor. For example, here, let's say I have this compound. I can use my translation model to generate several candidates, and I use my property predictor to see what are the what candidates actually make sense, does improve the property that I care about. Now these targets, these valid targets can be incorporated into the training set for the next iteration of training. And at the M step, we will just maximize the log probability of this augmented data set. You can already see substantial gain in translation and optimization tasks that I mentioned earlier. On top of this state-of-the-art graph-based method, you can still gain over like 10% accuracy improvement just by adding more data. So this really shows the difficulty of the graph translation task. The model kind of consistently improves if you add more and more data over the training process. And there is this more surprising fact. Interestingly, this augmentation technique is kind of robust to the property predictor. In the real life, you will never get this perfect property predictor to guide your model. So here we experimented with different levels of degraded property predictor to guide our translation model. So, and you can see on the two charts that I put on the slide, target augmentation still improves even if you have an imperfect predictor. We suspect this is because generating molecules is hard in general, and even just weak or noisy signals can still bring improvements to our translation model. So just for a summary, molecules are structured objects that provide a rich domain for developing machine learning tools. I'm just touching upon just one facet of this whole problem space that I put in earlier slide. There are many other applications, for example, reaction prediction and so on, that are also very challenging and interesting from the graph representation learning perspective. The key underlying challenge shared with other areas involve generation and manipulation of these diverse objects. And we can see from the practice, these machine learning-based molecular design methods are becoming more and more viable to drug discovery. But there are still a lot of challenges remain. For example, effective multi-criteria optimization that I mentioned. There's also challenges in incorporating 3D features or physical constraints into the model. There's also a general concern of generalization to new unexplored chemical spaces or domain transfer. There's also a lot of concerns about interpretability, how those property predictors actually work. What is the rationale behind the property predictor? What substructures does contribute to the chemical properties? So with that, I would like to conclude the talk, and I'm happy to take some questions.
Questions? Okay.
Hey, thank you. I think that's a really set of exciting results. I had a question about one of your slides where you showed the fusion of the two components when you're looking for the substructure and you want to join that to your current molecule.
Right.
You had a benzene ring and you had a thiophene ring, and you showed 6 different variants of how you could join that.
Right.
2 of those were actually unavailable, right, because it's in violation of the valency, and you'll never make them. But your model still chose to make the right molecule. I'm wondering if your model chose that because the underlying encoded data just did not show those other 2 types of molecules that would violate the valency of the sulfur and the thiophene, or was there some other heuristic that guided it?
Oh yeah, this is a really good question. Here, we constructed this vocabulary without adding those chemical constraints. But during decoding time, you can either turn on or turn off these constraints. So I think turning on these constraints during decoding will help avoiding those valency violation. But also, if, for example, so I constructed those vocabulary of these attaching configurations, some of them does not show up in the training set because it is just not viable according to the chemistry rules. Yeah. So the model will just learn to avoid them.
Okay, so you can start with sort of general open model as opposed to constraining it a priori, and it learns what it can and cannot do.
Right, yeah, it can learn sort of, not perfectly from the training data. Sure. Yes.
That's great, thank you.
Yeah.
You also showed some interesting results from, like, you mentioned that one of the antibiotics was also targeting another bacteria.
Right.
And as we all know, one of the major problems that's facing medicine is antibiotic resistance.
Right.
With your method, do you have a feeling for how well each of these drugs can target other bacteria? And when you also, the second question is, when you generate analogs that have different structures, do you think that will be able to be used to use both drugs for mediating antibiotic resistance?
Yeah, thanks. This is also an awesome question. I can answer this in two ways. Well, first, I think there are some data sets for explicitly modeling resistance, and we can incorporate those into our prediction models. So we can predict how resistant this molecule will be. The bacteria may easily adapt to this. And we also observed there are some data sets for example, from the Broad Institute that has, the inhibition according to many mutations of the biotargets. And we can try to find molecules that are inhibitive according to many of these mutants. And I think that's also one exciting application for multi-criteria optimization, that you want to optimize across multiple mutants. Yeah, I hope that kind of gives some, it's not there yet, but it's some interesting directions. Yeah.
Okay.
Over here.
Yeah, so it's a very interesting topic, so probably you can keep the discussions offline, right? So now I think you're going to discuss something related to benchmark data set.
Thanks. So now in the next few minutes before the next poster session, we're going to have another presentation, this time as opposed to an invited talk on a particular research topic. Instead, we're going to have Professor Yuri Leshkovich coming from Stanford University, my former advisor. He's going to be talking about a proposal, some thoughts, some preliminary steps towards a new set of benchmarks, set of open graph benchmarks to try to help improve graph representation learning by trying to provide a common resource, a common set of benchmark challenges for us to work on. So we're really excited to have Yuri present the initial work on this that he's been working on, led by him as well as members of his lab. And we're really hoping that's going to generate, hopefully, lots of questions, lots of discussion, both right after the talk as well as during the poster session and well into the evening. So, Yuri, take it away.
Thank you. So, as Will nicely said, this is really a community-based proposal, and it's at the early stage. So, as I go through, please think how you can help and how you can get involved. Let me start. So I really like the way Peter started the talk today in the morning, his invited talk, basically saying that graph representation learning, graph neural networks are one of the core sets of from the toolkit of deep learning. And as we have seen, doing representation learning over the relational data leads to state-of-the-art results in many different domains, right? Beyond just social networks, we looked at molecules, we saw about many interesting things in modeling physics and so on. So basically, using graph representation learning, we are achieving state-of-the-art in many domains. We have better applications, new insights, and new discoveries. And also, graph representation learning continues to increase, and it's the most increased keyword that I clear this year. But there is also a but. And the but is that if you look at what kind of data sets are we using to measure our progress, sometimes it's a bit embarrassing, right? So, for example, the standard molecule classification data set has 188 molecules, and our performances are in 90+ %. So it's basically any improvement is statistically not significant because the data set is so small. If you look at classical kind of node classification data sets like CiteSeer and Cora that many of the papers use, they are also kind of laughably small. So really, what's the observation, right? The observation is that to properly track the progress of this community, identify issues with current approaches, it is critical for us as the community to develop a diverse, challenging, and realistic set of benchmark data sets for machine learning on graphs, right? So only through this, we'll be able to track progress, we'll be able to identify deficiencies, issues with the current approaches, and extend them so that our models get better. So why do we need a new benchmark? One case I already made is that current focus is on small graphs, small sets of graphs in just a handful of domains, right? Currently, I would argue data sets are too small. Many times they don't contain rich node and edge features information. And because of this, it is hard to reliably and rigorously evaluate our algorithms. Because of the lack of the common benchmark data set for comparing different models' methods, basically every paper designed its own set of data sets, its own custom training test data set splits, and performances of the paper of the methods across the papers are not comparable. So it's even hard to make a sense of what kind of data, what kind of tasks given methods shine, and where other methods perform better. And another thing that is important is because we don't have standardized train test evaluation splits, we just resort to random data set splits. And in many domains, this is unrealistic. In terms of the applications, and many times it leads to over-optimistic accuracies. Because the question is also, how are we able to extrapolate to new unseen data points rather than just thinking of this as some kind of pattern recognition type systems? So in order to make this observation, what I was saying has been made over the years by many of us in the community. So the way we decided to organize this is to put together a steering committee of the members, of the people that I list here. And here is the proposal we came up with, and now we need to talk about how to execute on that proposal. So the proposal is to create the Open Graph Benchmark, which is a set of benchmark data sets for machine learning with graphs. The idea is that these are ready-to-use data sets with key tasks on graphs. And right now, the base tasks are node-level tasks, pairs of nodes, so link-level tasks, and entire graph, entire subgraph level task. Another important thing is that we need to provide a common code base to load, construct, and represent graphs. And this code base needs to be written in and compatible with popular deep graph learning frameworks like DGL, PyTorch, Geometric, graph networks, and so on. And what is also important is to have a common code base to evaluate the performance of the methods so that evaluations can be consistent across many different papers. And if we are able to do this, then we will be able really to focus on developing new machine learning methods, carefully tracking progress, and seeing basically making real progress rather than playing a game with different data sets. So the goal is to kind of focus on the center, which is the machine learning modeling, and use the OGB data sets, the data loaders, as well as the evaluators as a standard part of the pipeline. When we were designing this, when we were coming up with the design principles for this, we thought about 3 different dimensions. As I said, the first dimension is different tasks we would like to cover. For now, the obvious candidates are node property prediction tasks, kind of link property prediction tasks, and graph property prediction tasks. There are other tasks we would like to include along this task dimension, and we are very open for suggestions. Then the second dimension along which we thought is the is the data size, so that we've kind of captured the spectrum from relatively small data sets to medium size to really large ones, so that we can even also evaluate how much does additional training data, additional expressive power of our models, how does that come to improve performance. And then the last one is we would like to do this across a rich set of domains, and here I would say that graph learning, as you saw today from the talks, can be really richly applied across a wide number of scientific domains, applications, and so on. It's actually impressive how widely applicable these methods are. So, as I said, in terms of core tasks, right now we are thinking about nodes, links, and graphs. Node level tasks are like node classification, any kind of node property prediction. Link level tasks are link prediction, existence of a link, or predicting properties, types of links, which is what you may want to do in knowledge graphs, for example. For graph property level tasks, you can think of the previous invited talk, molecule classification, toxicity prediction, things like that. Then, in terms of domains, here are the ones we are thinking about and focusing on. So there is a rich area or opportunity for graph learning in natural sciences, meaning chemistry, biology, biomedicine. There is also a rich opportunity in terms of social information networks, knowledge graphs. This would be kind of online domains, recommender systems, things like that. And then, of course, there is a very rich opportunity in terms of using graph-based methods, for example, to model code that has more than just the linear sequential structure. And then, as I said, in terms of the data set sizes, we'd like to split things so that there are smaller, easier to work with data sets, as well as bigger data sets with hundreds of millions of nodes, or molecular data sets of tens of millions of molecules. So what I want to do next is walk through some of these candidate data sets, and most of them are prepared and already available. Others are in the process of being prepared. And then I will kind of wrap up, and happy to take questions and have a discussion before the poster session. So in terms of node prediction tasks, right, the goal is, given this kind of semi-supervised setting, part of the graph is labeled, part is unlabeled. We'd like to discover, predict labels of the unknown nodes. Here we are looking at many different domains. One is in computational biology, bioinformatics, thinking about multi-label binary classification of cellular functions of different proteins in protein-protein interaction networks. This has around 100K nodes. Then, this is a small data set. Medium size would be something 10x bigger, which could be the network of hyperlinks between Wikipedia articles, where classification would be the categorization of these Wikipedia articles. And then even a bigger data set comes from the Amazon product co-purchasing network, where again, this would be a multi-label binary classification into the product taxonomy of Amazon. Hopefully, we'll be able to add even bigger data sets here as well, but you see the domains are quite distinct. In terms of the link prediction, again, we have a set of increasing size data sets that go from anything from drug-drug interaction networks to human biomedical knowledge graphs, protein associations, all the way to the using a cleaned version of Microsoft Academic Graph with 200 million nodes of authors, keywords, papers, things like that. And the goal in most of these tasks is either doing predicting existence of an edge, or predicting some property of a given edge in the network. And when I say property, you can imagine this kind of multi-label, high-dimensional classification into the types of the edges, where edges can have multiple types at once. And then for the tasks around graph prediction, again, molecules are a very nice example here. So molecular graphs, we have synthesized a number of different molecular data sets. Interestingly, you can also represent code as a graph. You can represent computer code as a tree, and graph learning methods apply very nicely. So we have about several repositories with about 1 million little code snippets. And then we have also created a very unique data set of protein interaction neighborhoods across many different species, and classifying these subgraphs becomes an interesting task. Of course, we are open for other suggestions as well. The next point that I want to make is that in many of these domains, as you have seen, random splits are actually not necessarily the right thing to do, or random splits are too easy, right? Currently, if we look at what is the state of the art, basically our prediction accuracies on graph benchmarks are all between 75 and 95 plus, right? So we are always in the 90s, and this seems like we are doing this amazingly stunning job. Everything works amazingly well. We can just go home and enjoy life, right? But it doesn't seem to be the case, right? Prediction accuracies are often too optimistic under random data splits. So random data splits many times fail to represent what would actually one expect to find in the real world. In particular, if you think about natural sciences, experimental sciences, where data is experimentally collected, we are always doing out-of-distribution prediction, right? A scientist will never go collect exactly the same data that has already been collected before. A scientist goes collect some kind of related, new, different data. They do a new experiment. So we are always kind of trying to predict out-of-distribution. So having these types of splits becomes very important, that we really say we can generalize to unseen parts of the data distribution in some sense, right? So the point is we need meaningful data splits. So for example, in the OGB, we want to be very careful and mindful how are we creating these train test splits. For example, for molecular data sets, you can cluster the data sets according to their scaffolds, and then you learn on a certain set of molecular scaffolds and try to apply this to a new set. So again, the generalization is much harder because you are seeing novel structures you have never seen before at the test time. For example, for protein type networks, if we have multiple different species, multiple different organisms, we would like to generalize to a new organism rather than just kind of be able to interpolate inside a given organism. This becomes important as new organisms get sequenced, their protein networks get identified. We want to be able to apply our models, not wait that 3/4 of the network are labeled and only then we are able to come and help with machine learning methods. Same for code snippets. If you think about, right, we'd like to do this across different repositories, not just inside a given repository. So these types of splits become very important. So what I wanted to show is we created kind of a skeleton of a website called ogb.stanford.edu. We also have a mailing list of all the contributors at ogb@cs.stanford.edu, and this is a way to get in touch with us. What do we have so far is a pip installable software package that allows you to load data sets, load the splits, you do the predictions, and the evaluations come out. The idea is that this is very easy to use, and these OGB data loaders and evaluators are implemented both in PyTorch geometric and the DGL, the Deep Graph Library. So all you need to do is basically download this code, pip install it, and the data sets will be automatically downloaded, and everything should be easy to use. So the idea is that we have this set of easy-to-use data set loaders in PyTorch geometric. We also have standardized evaluators. So as you can see from these examples, it is very easy to measure performance according to the splits we have already prepared. So to kind of summarize or try to say what is the hope for the Open Graph benchmark, we hope this would be a resource for a range of machine learning with graph problems. We envision this to lead to many different applications, become a teaching resource, a data set of benchmark a database of benchmark data sets, a set of leaderboards or comparisons between different models, a realistic environment for new tasks, for new data sets, and an opportunity for new research in graph representation learning to occur and thrive. So, what is more to come? As the time goes, we are going to release more data sets, more tasks, and create leaderboards and benchmarks with the current models. How you can get involved is to provide feedback. Please come talk to me or anyone else on the steering committee. Provide ideas. Tell us what you think is needed. Please propose data sets, and then as a committee we will decide which data sets to include and which ones not, but please propose data sets. If you are willing to help in terms of benchmarking methods, models against these data sets, that would be super useful as well. Always feel free to contact us at the following email. And that is all I have to say, and I hope you find this community-based initiative exciting, and you will consider participating to it so that this field can continue to thrive and move forward. Thank you very much.
Yeah, we can take a couple of questions before we start with the poster session, if anyone has any questions.
Hi, Yuri. Yeah, this is a great initiative. I am Ankit from DeepMind Montreal. So one dimension which I found missing in the dimensions you told about different data sets is like the sparsity. And like we encounter it a number of times that the techniques which may apply to the dense graphs may not hold for sparse graphs. So do you think that to have that dimension, it is important? And if not, what are your thoughts on it? And or we should be incorporating the sparsity of the graphs as well in the future benchmarks?
That is a great question. The way perhaps I would respond is, I think it's an excellent point you are making. Our, in some sense, expectation was that this let's say, sparsity and other types of, diversity of properties of the data sets will come through the different application domains. And I agree that in certain application domains, the graphs will be kind of denser. In others, they will be kind of more like natural graphs, heavy-tailed, kind of small world, amazingly sparse. So hopefully these dimensions come in through the applications. And I think this way, this means it will also be realistic. But that's an excellent point.
Yes, thank you. Great initiative, should lead to a lot of progress. On the topic of proposing new data sets, we've already had for a few years the Prague Relational Learning Repository with about 80 multi-relational graph data sets, some benchmarking. I wonder what the relationship is between something like the Prague repository and yours. Did you already import the existing data sets, or is this just a wholly separate thing? Oh,
great point. So the point, I think, like, there is a bit of a, I think we need to be a bit careful, right? Like the Prague repository is 80 data sets. My group released, I think, about 150 different network data sets. And then again, it becomes so many different data sets and so many different little intricacies that it feels like there is no common data set. So our goal is not to release 200 data sets. Our goal is to release, I don't know, 10. Right? To basically really think through and say, this is what we think is a common set of things we need, rather than say, here is 300, dear researcher, figure it out. Yeah. But thank you for the pointer. Thank you for mentioning it.
So first, it's a great initiative again, so I think everyone would agree with that. One thing that I found missing is talking about the node features. Basically, all the methods rely on having some kind of node features, and there's no standard way of having them. Some datasets come with natural ones, some don't. What is your opinion about this axis?
That's a great point. Our goal is to provide as rich node feature information or node attribute information as possible. And I would say that in most cases, you actually have this, and it should be very useful. So our goal is to do a really good job and provide that data as much as possible.
Okay.
Yeah, thank you.
So I think, unfortunately, we'll have to switch to the poster session at this point, but I really encourage people to catch Jure, come up to the front, come talk with us, come talk with other members of the steering committee. But for the sake of allowing all of our wonderful contributed posters to have time to present their work, I will switch to the session now. So we will do that for the next hour. So please enjoy the posters, grab a coffee if you need one, and we will begin again at 4:15 for our remaining 2 invited talks of the day, and then our final short presentation on the Deep Graph library before we wrap things up.